Hi, this is Mr. Cappert. This goes along with conservation of energy worksheet for the Trebuchet project. Now, hopefully you've been introduced to this in physics. If you haven't, maybe I'll need to do a little bit more review in the coming days here. So the law of conservation energy just says that energy is transferred from one form to another, not created or destroyed ever. This is a very important law within physics and used quite a bit in engineering. Now, with our trebuchet, we're going to have a transfer of energy from one form to another. Now, the reason why we have a counterweight in this project is because that is where our input of energy comes from. All of the energy at the start before you fire it comes from the fall of this counterweight. So energy due to position, due to height, is called gravitational potential energy. Due to its height, this counterweight has energy stored. How you find that stored energy is you take the mass of the counterweight times the gravitational constant. That's always going to be 9.8 meters per second squared. Maybe you've used 10 meters per second squared in the past. 9.8 is more accurate. Then times the height. In this case, we're trying to find a change, so you would put the change in height, how much it fell by, in order to find the potential energy. So this potential energy is not destroyed as it falls. As it falls, it's actually transferring that energy to the kinetic energy of your projectile. We're going to throw a marble. So as it falls, the counterweight's going to have less and less energy. The marble is going to have more and more energy, which is what we want. We want to throw the marble. So kinetic energy is a different type of energy. It's energy due to movement. And you find it through taking 1/2 times its mass. In this case, we're going to use the mass of the marble. Don't use the counterweight. Common mistake. Times its velocity squared. Now, I forgot to define energy. You may have not had that defined to you before, but it's the ability to do work. Energy is the ability to do work, which means you can apply a force and move something. So there's all sorts of energy. Chemical energy is in gasoline. Gasoline has the potential to create a force that drives a car. In our case, this potential energy has an ability to fall, move a distance, and cause an increase in kinetic energy of the marble. So we're transferring between those two things. We're making a lot of assumptions, which this happens in engineering all the time. These things are too difficult to figure out typically. So we're going to end up with the max range. Everything's going to be perfect when we do our equation. So we won't be able to throw it as far as what our calculations will say because we are assuming perfect world. So things that would actually throw this off is some of the energy should go into bending the arm, for instance. We can't consider that too hard to do. Rigidly fastened to the ground, all right, that makes our equations easier. No friction. So we're saying all of that energy from the counterweight falling goes to the projectile. None of it is turned into heat through friction. No air resistance. That would be way too hard to figure out. So we're not going to factor in wind or air that should be slowing down our marble or even the arm itself. So an example problem here. This is one of the two problems on the back of your worksheet, problem 3 and 4, I believe. Very similar to those. Calculate the launch velocity of a 0.00496 kilogram marble if the trebuchet's counterweight has a mass of 1.7 kilograms and falls 0.15 meters. This is actually the mass of the marble we're using. The units are important here. The electronic balance finds things in grams. In order for the units to all check out, we need to use kilograms and meters. We can't use inches here or centimeters. You must use these units. And these are all really accurate numbers, actually. These all make sense for this. So the first step, though, in order to finding this velocity is to find the change in the gravitational potential energy of the counterweight. So use that potential energy equation to solve for the change in potential energy of the counterweight. So mass of the counterweight, right, times this gravity, which is always the same, and it's written on your worksheet, times how far it fell. It fell 0.15 meters. That gives you 2.499 joules. Joules is the unit of energy. Now B seems trickier than it is. People always get this wrong. What is the kinetic energy of the projectile as it leaves the trebuchet? Everybody wants to use this equation. Kinetic energy equals 1/2 mv squared. The problem is we don't know velocity. And so I would say 90% of my students stop and are unable to do this problem. You need to realize that energy is conserved. The energy that we just found, this potential energy, all of this is not destroyed as it falls. It is being transferred to kinetic energy. Thus, the kinetic energy of the marble is equal to that potential energy we just found. So what I'm saying is all of this potential energy is being transferred to the energy of motion, kinetic energy of the marble. Once again, we're assuming perfect world, that this isn't bending. We don't have friction, those types of things to make our equations easier. And then last part, you can get to the launch velocity of your projectile. You can use this equation, kinetic energy equals 1/2 mv squared. I'm not going to do the whole thing for you. You know the kinetic energy, you found that in part B. You know the mass. Remember, we're talking marble projectile, so you want the mass to be the mass of the marble. And velocity is what you're trying to solve for. So plug those in, use algebra to then solve for the velocity of the projectile, or marble in this case. Well, that does it for this video. Let me know if you have any more questions.